You think mountains have a shape. Look at one. Any mountain, the Alps, the Rockies, the Himalayas, you see something, a silhouette against the sky, peaks and ridges, valleys and slopes. You could draw it, you could photograph it, you could describe it. That's the shape of the mountain, right? Wrong. What you're seeing isn't the shape of the mountain. It's the shape of the mountain at one particular scale. Change the scale and you change the shape. Zoom in and new features appear. Zoom out and features disappear. The mountain you think you're looking at is not a fixed object with a fixed form. It's a different object at every scale you examine it. This is not an optical illusion. This is not a limitation of your eyes or your instruments. This is a fundamental property of what mountains actually are. Mountains don't have a single true shape because mountains exist across scales, and at each scale they reveal different structure. Let me show you what I mean. Imagine you're flying in an airplane at 30,000 feet. You look down at a mountain range. You see broad shapes, major peaks, large valleys, the general contour of the terrain. That's the mountain range at airplane scale. Now imagine you're hiking on that same mountain. You see something completely different. Boulders the size of cars, rock faces with cracks and ledges, small ravines that were invisible from the air. The terrain is far more complex than it looked from above. Now imagine you're an ant crawling on one of those boulders. You see something different again. Tiny crevices, mineral crystals, microscopic roughness that would be completely invisible to the hiker. Which view shows the true shape of the mountain? The airplane view, the hiker's view, the ant's view? The answer is none of them. And all of them, each scale reveals real structure that actually exists. None of the scales is more true than any other. The mountain is all of these shapes simultaneously. This should disturb you. We're taught that objects have shapes, fixed, definite, measurable shapes. A ball is round, a box is rectangular. A mountain is what? We want to say the mountain is something, but what we discover is that the mountain is different things at different scales. This is what I spent my career trying to understand, not the shapes that simplify when you zoom in, but the shapes that maintain their complexity across scales. Shapes that refuse to settle into a single definite form, no matter how you examine them. Mountains are the perfect example, or they're not smooth objects with a little roughness added on top. They're fundamentally rough at every scale. The roughness isn't noise. The roughness isn't error. The roughness is what the mountain is. Here's how I want you to think about this. Take a piece of paper. Crumple it into a ball. Now try to describe its shape. At large scale, it's roughly spherical, but look closer. You see folds and creases everywhere. Look closer still. Each fold has smaller folds. Each crease has smaller creases. The complexity doesn't disappear as you zoom in. It transforms into different complexity at smaller scales. Mountains work the same way. The processes that created them, geological forces operating over millions of years, don't produce smooth surfaces. They produce rough surfaces, fracturing, erosion, weathering. All these processes create structure at every scale. When a rock fractures, it doesn't break along smooth planes. It breaks along irregular surfaces that themselves have irregular features. When water erodes rock, it doesn't carve smooth channels. It carves channels with rough edges that have their own rougher edges. When freeze-thaw cycles weather a surface, they don't produce smooth degradation. They produce pitting and cracking at every scale. The roughness cascades down through the scales. Large-scale roughness creates the conditions for medium-scale roughness. Medium-scale roughness creates the conditions for small-scale roughness. The same types of processes operating at every scale produce the same types of structure at every scale. This is self-similarity. Not exact self-similarity, where the small looks identical to the large, but statistical self-similarity, where the small has the same character as the large, the same roughness, the same complexity, the same refusal to simplify. Now you might ask, so what? Mountains are rough, big deal. Why does this matter? It matters because it breaks how we measure things. Consider a simple question. How long is the coastline of Norway? This seems like it should have a definite answer. Get a map, measure the coastline, report the number. Done. But here's the problem. The answer depends entirely on the scale of your measurement. If you measure with a ruler 100 kilometers long, you get one answer. Your ruler skips over all the fjords and inlets smaller than 100 kilometers. You're measuring a simplified coastline. If you measure with a ruler 10 kilometers long, you get a larger answer. Now you're capturing more of the indentations. More detail means more length. If you measure with a ruler 1 kilometer long, larger still. Even more detail, even more length. If you measure with a ruler 1 meter long, you get an enormously larger answer. Now, you're capturing tiny irregularities invisible at larger scales. The smaller your ruler, the longer the coastline becomes. There is no true length of the coastline of Norway. The length depends on the scales of measurement. This is not a measurement problem. This is not a failure of our instruments. This is a fundamental property of coastlines. They have structure at every scale. So there's always more length to discover at smaller scales. Mountains have the same property. How rough is a mountain surface? Depends on the scale. How much surface area does a mountain have? Depends on the scale. How complex is the terrain? Depends on the scale. Every measurement you make of a mountain is a measurement at a particular scale. Change the scale, change the measurement. There is no scale-independent answer because the mountain itself is not scale-independent. This has profound implications for how we make maps and models. Every map is a choice of what to include and what to leave out, a choice of scale. When you make a map of a mountain, you're not capturing the true shape of the mountain. You're capturing the shape at the scale you chose. A topographic map at 1 to 100,000 scale shows major features, peaks, ridges, major valleys, but it completely ignores structure smaller than about 100 meters. That structure exists. It's real. It affects hikers and climbers and water flow and erosion. But the map doesn't show it because the map chose a scale that excludes it. A detailed survey at 1 to 1,000 scale shows much more. Individual boulders, small gullies, fine structure invisible on the broader map, but it still ignores structure smaller than about a meter, and it only covers a tiny area. There is no map that shows everything. There cannot be such a map. Because the mountain has structure at every scale down to the molecular level. To capture all of it, your map would have to be as complex as the mountain itself. At that point, it's not a map, it's a copy. This is the fundamental limitation of all models of rough natural objects. Every model chooses a scale. Every model ignores structure below that scale. Every model is therefore incomplete. This isn't a failure of our modeling techniques. It's a recognition of what rough objects actually are. They contain more information than any finite model can capture. They're inexhaustible. Now, here's where I want to shift your thinking. For centuries, we've asked questions like, what is the true height of this mountain? What is the true shape of this coastline? What is the true area of this lake? These questions assume there are true answers independent of scale. They assume that if we measure carefully enough, we'll find the definitive number. But for rough objects, these questions are wrong. They're not unanswerable. They're the wrong questions to ask. The right question is not what is the true measurement. The right question is, what is the measurement at this scale, and what scale is appropriate for my purpose? An emotion is, if you're flying an airplane, the large scale shape of the mountain matters. The small scale roughness doesn't. You need the airplane scale map. If you're climbing the mountain, the medium scale features matter. The handholds, the ledges, the cracks, you need the climber scale description. If you're studying erosion at a specific site, the small scale roughness matters. You need the geologist's detailed survey. Each scale is right for its purpose. No scale is right for all purposes. The question, what is the true shape, has no answer because there's no purpose-independent truth about shape. This is a profound shift in how we think about measurement and knowledge. Classical science assumes that better measurement gets you closer to truth. Measure more precisely, and you find the true value hiding behind your measurement error. But for rough objects, better measurement doesn't converge to a fixed answer. It reveals more structure, more complexity, more detail that was invisible before. The true value isn't hiding behind measurement error. There is no scale-independent true value. This doesn't mean measurement is useless. Measurement at a chosen scale is perfectly valid. It tells you about the object at that scale, but it doesn't tell you about the object at other scales, and it doesn't tell you anything scale-independent because there's nothing scale-independent to tell. Now, let me introduce a concept that captures this scale-dependent complexity. Fractal dimension. In classical geometry, dimension is a whole number. A line is one-dimensional, a surface is two-dimensional, a volume is three-dimensional. These dimensions tell you how objects fill space, but rough objects don't fit neatly into integer dimensions. A coastline is more than a simple line because it's so convoluted that it partially fills a plane, but it's less than a surface because it doesn't actually cover area. A mountain surface is more than a simple two-dimensional surface because it's so rough that it partially fills volume, but it's less than a three-dimensional solid because it's still a surface. These objects have fractional dimensions, dimensions between the integers. A coastline might have dimension 1.2 or 1.3. A mountain surface might have dimension 2.3 or 2.4. What does this dimension say? Distanza insanscides ort nomon zimse elas kur doachers tensia or zorzde. It measures the roughness. It measures how complexity changes across scales. It measures the rate at which measurements like length or area grow as you examine the object at finer and finer scales. A dimension of exactly 1 means a smooth curve. Measure at finer scales, the length stays constant. No hidden complexity. A dimension of 1.2 means mild roughness. Measure at finer scales, the length grows slowly. Some hidden complexity. A dimension of 1.5 means significant roughness. Measure at finer scales, the length grows faster. More hidden complexity. The fractal dimension captures in a single number how the object behaves across scales. It tells you something fundamental about the object that no single scale measurement can reveal. And here's the remarkable thing. Natural objects cluster around characteristic fractal dimensions. Mountain surfaces tend to have dimensions around 2.1 to 2.4. Coastlines tend to have dimensions around 1.1 to 1.4. Cloud boundaries have dimensions that reflect the turbulent processes that formed them. The fractal dimension is not arbitrary. It emerges from the processes that created the object. It's a fingerprint of the underlying physics. Different geological processes produce different roughness. Volcanic mountains have different fractal dimensions than fault block mountains. Young, tectonically active ranges have different dimensions than old, eroded ranges. The roughness tells you about the history. This is why fractal geometry matters. It's not just a mathematical curiosity. It's a tool for understanding natural objects as they actually are, rather than as simplified, smooth approximations. Let me return to the original question. Why don't mountains have a true shape? Because shape is not a fixed property of a mountain. Shape is a relationship between the mountain and the scale at which you examine it. Change the scale, change the shape. The mountain doesn't change. Your perspective changes. And with rough objects, perspective is everything. This is deeply different from how we think about manufactured objects. A ball bearing has a true shape. It's a sphere. Measure at finest scales and you find it's very close to a perfect sphere with tiny deviations. The shape converges to a definite answer. But natural objects formed by natural processes don't work that way. They're rough at every scale. Their shape doesn't converge. Their complexity doesn't simplify. They remain scale dependent all the way down. Now here's what this means for how you see the world. When you look at a mountain and see a shape, you're seeing one slice of a multi-scale object. The mountain is simultaneously all the shapes it has at all scales. Your perception picks out one, but the others are just as real. When a scientist makes a model of terrain, they're choosing which scales to include and which to ignore. The model isn't the traverse the territory. It's one perspective on the territory, a perspective defined by scale. When anyone claims to have the true description of rough natural object, ask them at what scale, because the answer depends on There's no privileged scale that gives the true answer. This is humbling. We want definite answers. We want true shapes and exact measurements. We want the world to be simpler than it is. But the world is rough. Natural objects have structure at every scale. Complexity doesn't disappear when you look closer. It transforms into different complexity. And this scale-dependent richness is not a problem to be solved. It's a fundamental feature of how nature builds things. Classical geometry gave us tools for smooth shapes, shapes where measurement converges, where there are true values, where scale doesn't matter beyond a certain point. Fractal geometry gives us tools for rough shapes, shapes where measurement depends on scale, where there are no scale-independent values, where every scale reveals new structure. Both geometries are valid. Both are useful, but for natural objects, or for mountains and coastlines and clouds and trees, fractal geometry is often more appropriate. It captures what these objects actually are rather than what we wish they were. The mountain you see from your window doesn't have a true shape. It has infinitely many shapes, one for each scale of examination. Each shape is real. Each reveals genuine structure. None is more true than the others. This isn't a limitation, it's a liberation. It frees you from asking the wrong questions. It points you toward the right questions. Not what is the true shape, Wulan, but what is the shape at the scale that matters for my purpose. When you ask the right question, you get useful answers. When you ask the wrong question, you get confusion and frustration. Mountains taught me this. Their refusal to have a single shape forced me to develop new mathematics. Mathematics that embraces scale dependence rather than fighting it. Mathematics that measures roughness rather than ignoring it. Mathematics that sees multi-scale complexity as fundamental rather than as noise. This mathematics applies far beyond mountains. It applies to any rough object, any system with structure at multiple scales. Financial markets with fluctuations at every time scale, turbulent fluids with eddies at every size, biological structures with branching at every level. The principle is the same. These objects don't have single true descriptions. They have scale-dependent descriptions. The right description depends on the right scale, which depends on the right purpose. No single scale captures the truth because there is no single truth to capture. There is only the truth at each scale. Infinitely many truths for infinitely many scales, all equally real, all part of what the object actually is. This is what mountains teach us. This is why they don't have a true shape. This is why the question, what does a mountain really look like, has no answer. The mountain really looks like all of its appearances at all scales. That's what mountains are. That's what rough objects are. That's what nature actually produces. And once you see this, once you really see it, you stop asking for single answers to multi-scale questions. You stop expecting convergence where there is none. You start seeing the world as it actually is, rough, complex, scale-dependent, and infinitely rich. Not comfort, not simplicity, truth,